it should have low notch sensitivity factor. So it should have a good heat treatment properties. And also, last one, it should have high wear resistance properties. It should have high wear resistance properties. So first thing is it should have a high strength. Okay, so because if the material is of a very high strength, so you can go for smaller dimension shaft to carry the large power. Okay. Second one, it should have a good machinability because so based on the dimensions uh, to decrease the size of the material to the required diameter, it should give a good machinability. Along with that one, so as you need to place some pulleys, gears, and some components over the shaft, so it should have a good machinability. That means you can easily cut the keyways or you can easily drill the holes, okay, as to mount the gears, pulleys. Okay. Next, low notch sensitivity factor. So as you're going to provide some discontinuity over the shaft, that's what for mounting purpose, you may going to cut the keys, you may going to drill the holes, or you may going to say make some splines over it. Okay. So as you're going to change the cross section, so it's going to give some stress concentration. So that's what it should give some low stress concentration. So where it has coincident with the notch sensitivity Q factor. Fourth one is it should have a good heat treatment properties because the shaft is going to be used in different environments. So that should have a good heat treatment properties. So wear and tear may occur if it is mounted in a bushing. Okay. So next, it may be used in some. One example I can put for this heat treatment properties a crankshaft. Okay, crankshaft which is going to be used in IC engines. So it has enormous amount of heat is going to produce so that it is transmitted to the crankshaft through the connecting rod as well as piston. Okay. So next, it should have a high wear resistant properties. As I said, it's going to be mounted between the bearings as well as journals. Okay. If it is mounted over the bearings, then no problem of wear and tear. If it is mounted in a bearing, there is no problem of wear and tear. But if it is mounted in a journal, so then wearing of the shafts will take place. Wearing of the shaft will take place because of the friction between the journal lubricant as well as this shaft material. Okay. So now these are the requirements of a shaft material. Now let us go for shafts material here. So you're going to get some standard shaft materials. Okay. You're going to get some standard shaft materials. So based on Indian standard designation, so the preferred steel materials for manufacturing of shafts. Okay. So one is 40C8. 40C8 is one. Second one is 45C8. Next 50C4 and 50C12. 50C12. When a strength of the high strength is required, so then an alloy steel such as nickel, chromium. ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಅಕಸ್ಮಾತ್ ಮಾತಾಡ್ಬೇಡ. ಹ್ಮ್ Okay, so now we'll see standard sizes. Okay, so now standard size are available from Design Data Handbook. That is what table number 3.5a. That is what chapter number 3. So design of shafts. Okay, so here the increment of shaft diameters are given here: 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, so up to some stage they have an increment of 2 mm, and from some stage it has increment of 3 mm, and from some stage it is increment of 4 mm, and from some stage onwards it has some random increments here. Okay, just look out here. So 6 mm to 600 mm diameter standard shaft sizes are available in market. Okay, so now the standard length of shafts are 5 meter, 6 meter, and 7 meter. Okay, the standard size of shafts are 5 meter, 6 meter, and 7 meter. Okay, so you can suppose if you got a diameter of the shaft. Okay, let us go for here. Suppose if you got a diameter shaft as 11 mm. Okay, suppose if you got a shaft diameter as 11 mm, so you go for shaft as, let us go here. So in calculations, if you got a diameter as 11 mm, okay, so now you need to go for selection of standard size. T has to be 12 mm from data handbook. Okay, from design data handbook. Right, so now you should not go for less than 11 mm. Okay, you should not go for less than 11 mm. Suppose if you gone for 10 mm here, 10 mm, so if you recheck the induced stress is more, because as you reduce the diameter calculation, that means the diameter as 11 mm to 10 mm. Okay, now how you got this diameter? So based on the allowable stress only you got this 11 mm diameter. Okay, then if you've gone for lesser than this one, so induced stress will be more than the allowable stress. So now let us go for design of shafts. You have two criteria here. One is a strength base, another one is a rigidity base. Okay. No. So you have two criteria. One is strength base here, another one is rigidity base. Okay. Now, before we want to start this design, so let us check out what are the differences are going to induce, are going to occur, are going to produce by a shaft when it's subjected to the different loads here. Okay. So first one is only shear stress. Only shear stress. Okay. Second case is only bending stress. Only bending stress. Third one is shear stress and bending stress. And bending stress. Okay. Now, example I can quote for the pure shear stress. Okay. Pure shear stress. Okay. This is what only power transmission. Only power transmission. Okay. If a shaft is used to transmit only the power, then the shear stress is going to induce in the shaft. induced in the shaft. Okay, as it is subjected to the torque, so it's going to give some torsional shear stress. Now, only bending stress, so it is subjected to only carries the load, only carries the load, okay, and no power transmission, and no power transmission. So, example here, axle, example here, it is a motor shaft, okay, it is what a motor shaft. Next, so third case is shear stress and bending stress. Shear stress and bending stress. So now in this case, so this is also going to transmit the power. Okay, it is also going to transmit power and also carries the load. Also carries the load. Okay. Suppose if a shaft is going to use for power transmission as well as for carrying the load, okay, then it is going to be subjected to the both type of stresses. That is what shear stress and bending stress. So let us consider for third case. So let us take a shaft. Okay, let us take a shaft here. So which is mounted between two bearings. Which is mounted between two bearings. Okay, so which is going to receive the power from one source. Okay, and it is going to transmit to the another source. Let us consider. So at exactly middle portion, it has an gear here. It has a gear. Okay. So where it is going to transmit the power to some other driver here. To the some other driver. Okay. Let us look out here. Now you have an motor here on left side. You have a motor, right? This is what a bearing you have supported here in a bearing. This is what one more bearing here, right? This is what a gear. This is what a gear. And now you just look out here. Now this is what a driven. This is a driver. Okay. Now as power is going to be transferred from this motor to this shaft here, this shaft here, one it is subjected to the torsional movement. One thing is it is subjected to the torsional movement, right? Now, as it needs to transmit the power from driver to the driven here, so it has to transmit the power action of by the action of the tangential load as well as the radial load. Tangential load as well as the radial load. Okay. So now what happens here? So this tangential load try to push off this driven more with more force. Okay. And that case is what happens. So this shaft is going to bend. This shaft is going to bend. Right now, just look out here. If you go for replicating this system in a free body diagram form, okay. Now I'll just draw a line diagram here. I'll just draw a line diagram. Now this is what a shaft. Now it has to transmit the tangential load to the driven. Okay. So now this is also subjected to the what? It is subjected to the torque T. Okay. Now due to this torque, it is subjected to the shear stress. Okay. Now if you consider the placement of this shaft, it is what now it has been fixed, or sorry, it has placed between two supports. Okay. That is what support A and B. Okay. Now exactly at center, it is subjected to the tangential load. Okay. Now if you consider this load, now what happens here? So this is going to bend this shaft in this form. Okay. Now if the shaft is going to bend, this is going to reproduce a bending stress. Okay. and this torque T is going to reproduce or is going to produce the shear stress tau. Now it is subjected to the both shear stress and bending stress. Okay. So now let us look out a design of shafts based on strength. Now, so when you are going to define a strength, so strength is equal to the it's the stress. Okay, strength is equal to the stress. Okay, so now strength means it is always the shear strength. Always it is what a shear strength. Okay, which is equal to the shear shear stress of the shaft material. Now, let us consider the torsional shear stress relation here. Torsional shear stress relation. What is the torsional shear stress relation? So T by J equal to tau by R, which is equal to G theta by L. Okay? Which is equal to G theta by L. Okay? Now I can rewrite this one. Okay, I can just rewrite this one. Suppose now let it. We will first notify the what is the meaning of T, J, and all those things here. So now where T equal to torque or torsional moment, torque or torsional moment. This is what in Newton mm. So J is polar modulus of the shaft. Okay, this is what mm to power of 4. Next, tau is what? It is a shear stress. Tau is shear stress. This is what Newton per mm square. So R is what? Radius of outer ring. Okay, or radius of ring element. Okay. Now G is what? Modulus of rigidity. Modulus of rigidity. Now this is what Newton per mm square. Okay. So theta value is what? It is angular deflection. Angular deflection. Okay. So this is in terms of radians here. This is in terms of radians. So L is unit length of shaft. Unit length. Okay. We can just go for unit length. Okay. Right. Now this is what in terms of either mm or in meter. Okay. Now you must take a care here. So all units should be in a one format. Okay. If you gone for Newton torque as a Newton mm, then all these things are to be in form of mm. Okay. You should not go for one unit as a meter, another unit as a mm. Suppose if you are going to find the diameter of shaft based on this relation, so then this is called as design of shaft based on strength. This is what design of shaft based on strength, right? Now let us go for the calculation of shaft dimensions. Now tau is what? Let us consider so tau is allowable shear stress of shaft. Okay, shear stress of shaft. Okay, now T is the applied torque on shaft, on shaft. Okay. What is the relation you are going to get here? Now, T by J equal to tau by R, or R. Okay. So tau by R equal to T by J. Right. Now let us substitute here. Let us substitute. So T by J equal to tau by R. Now what is the value of J for circular cross section? This is what? Pi d to power of 4 divided by 32. Divided by 32. Now value of R equal to what? D by 2. Value of R equal to D by 2. Why need to go for R equal to D by 2? Because so the distribution of shear stress. Okay. So the distribution of shear stress is maximum at outer surface. On this outer surface is what? The shear stress is maximum here. Tau is maximum. So at R equal to 0, tau is 0. Okay. R equal to 0, tau is 0. Now, let us substitute. Let us substitute here. Okay. So now T divided by pi d to power of 32 equal to tau divided by d by 2. Okay. Our intention is to find out the diameter now. That is what dimensions. Okay. Now, so let us take here. So T divided by tau equal to pi d to power of 4 divided by 32. Okay. So now this is what divided by 2. If you simplify here, T by tau equal to pi d cube divided by 16. Pi d cube divided by 16. So again, if you rewrite for diameter d, so what is the equation you are going to get here? So now this pi d cube equal to 16t divided by tau. This is d cube equal to 16t divided by into tau. Now d equal to cube root of 16t divided by pi into tau. Now you can use this equation to find out the diameter of shaft when you know the shear strength as well as the torque transmitted over the shaft. Right. So now to get this equation, you just refer the design data handbook here. Okay, now we can refer equation number, okay, 3.4a. 3.4a. This equation is suited for hollow shaft. Okay, this equation is suited for hollow shaft. If you want to find the diameter of a solid shaft, then you substitute k equal to 0 here. Okay, so now I'll rewrite this equation in PPT. Okay, so now you can just refer equation number 3.4a, design data handbook. Okay, the thing is that substitute k equal to 0 for solid shaft, for solid shafts, right? This is what based on the strength, based on the strength. Okay. Next, suppose if it is subjected to bending stresses, if it is subjected to bending stress, right? So example, you can go for consider a axle here. Okay. Now let us take here let us take, so an axle is there which is going to support the load. Okay, so it is a non-rotating member. Axle is non-rotating member. Now this is what F. Okay, now what is the bending stress relations here? Bending stress relations. So bending stress relation, sigma B by Y equal to E by R equal to M by I. Okay, sigma B by Y equal to E by R equal to M by Y, or M by I equal to sigma B by Y equal to E by R. Okay, just uh, write in a such a way that where you can easily remember it. Where you can easily remember it. Right. Now, again, if you want to find out the dimensions based on the modulus of elasticity, okay, based on modulus of elasticity, now you can just consider this portion based on modulus of elasticity. Okay, suppose if you want to find the dimensions based on the strength, you can just consider this one equation and this one equation. Okay, so now based on strength, this is what M by I equal to sigma B by Y. Okay, sigma B by Y. So now Y is what? D by 2 here. Okay, I'm not going to write all the things here. I think you know. So sigma B is allowable bending stress in a megapascal or in Newton per mm square. Y is distance of outermost layer here. So M is bending moment. Okay. So I is moment of inertia. Moment of inertia here. Now this value is Newton meter. Okay. This value is mm to power of 4. Now this has to be Newton mm also. Okay. So E equal to Young's modulus. E equal to Young's modulus. This is what Newton per mm square. So R is radius of curvature. Okay, in EMN. Okay. Now, as going for based on strength here, so now we can just substitute if sigma B is the allowable bending stress. So M is a bending moment. Okay, M is the bending moment. Okay. Now let us write equation here. So M, I'll go for FL by 2 here. Okay, as the bending moment. I is pi d to power of 4 divided by 64. Okay, so this is equal to what? Sigma B divided by d by 2. Now if you rewrite this equation, okay, if you rewrite this equation for this case, okay, otherwise we'll just go for M here, M. Now what is the equation you're going to get here? M divided by sigma B equal to pi d to power of 4 divided by 32 is what? D by 2. If you simplify, M divided by sigma B equal to pi d cube divided by 32. Okay. Now diameter D is what? 32 m divided by pi into sigma B. It is what? Cube root. Okay. It is what? Cube root. Okay. You can just look out in data handbook. Okay. Now we can refer equation number 3.4b here. Okay. So design data handbook. You refer equation number 3.4 B. And for solid shaft, substitute K equal to 0. Substitute K equal to 0. Right? So next criteria, so design based on rigidity. Design based on rigidity. Now, based on rigidity, okay. So now T by J equal to G theta by L, okay, G theta by L. Now, if you substitute the value of J here, okay, so T divided by pi d to power of 4 divided by 32 equal to G theta by L, okay. So now if you rewrite this equation for D, okay, let us see what happened here. Okay? So 32 TL divided by G theta into pi to the fourth root. This is what diameter. Now we can just refer design data handbook. Okay. So equation number, I think it has gone for 584 TL. Okay. It is in terms of radians here. It is in terms of radians. Okay. Now you're going to get this equation. You're going to get this equation. If it is a we design based on rigidity. This is what G. Okay? Based on rigidity. Or else you refer equation number. This is what 3.2. This is in terms of degree here. Okay, this is in terms of degree. Okay, that is what 584 TL. Okay, so theta equal to 584 TL divided by G d to power of 4. Now theta is to be what in terms of a degree. Okay, in terms of degree. Okay, so then only we are going to get the value of D here. So L is to be substituted in relation with the torque here. If you substitute a torque in Newton mm, okay, then L has to be in mm, okay. Then you are going to get D has to be in mm, right? D has to be in mm. You must take care while substituting units for calculation purpose. Okay. Next thing is if it is subjected to both, okay, if the shaft is subjected to both stresses, that is shear stress and bending stress. Okay, bending stress. Now in this case, you need to design shaft based on the failure of theories or theories of failures. Theories of failures. So one is you need to go for maximum principal stress theory. And second one is maximum shear stress theory. Maximum shear stress theory. Right? Now, so let us look out. So based on maximum shear stress or principal stress theory, what is the equation you are going to obtain here? Okay. So now based on maximum principal stress theory. Now sigma 1 equal to Okay, so sigma x plus sigma y divided by 2 plus square root of sigma x minus sigma y divided by 2 square plus tau xy square. Okay, this is the principal stress theory. Okay? Now, if sigma x equal to sigma b, okay, and tau xy equal to tau, okay, now sigma 1 equal to sigma a. Okay? Now where sigma x equal to sigma b, now this is what a bending stress here, bending stress, and tau xy